To everyone joining me for this video on absolute or global extrema, I thank you. I am Mr. Ish. Thank you for joining me for this video. We are looking here at the definitions of absolute maximum and absolute minimum. You can call them likewise global maximum and global minimum. Those are synonymous terms. For any function having a certain point which is being evaluated as a critical point or as an end point, if that point is placed into your function, it leads to the highest output from that function over that interval, then that represents an absolute maximum. Remember, you're looking here at range values, your output, your y values. That same point, if placed into your function, your original function, it generates the lowest output or the lowest y value, the lowest range, then it represents an absolute minimum. Any other critical points which are open for evaluation, if they're not these, then they could very well be relative maximum, relative minimum, or perhaps nothing at all other than just a point on the curve. Look here at the interval, it's a comma b. You have to contrast absolute or global extreme values with relative or localized extreme values. With regards to these absolute values, you can only have one of each, either a maximum or a minimum, but with regards to the relative, you could have several or perhaps none at all. If you look here, I've identified points A, B, C, D, and E. These could potentially be labeled as something from an interval A to B. This right here, A, your start of your interval actually leads to a good endpoint. Your end of your interval leads to a good endpoint. There's a critical value here which leads to this. There's a critical value here which leads to that, and another critical value leads to that. We have to identify these as such. When I'm looking at all of these, I'm looking at in terms of the y-axis values. This clearly leads to the highest value, and this right here is an absolute maximum. Then I'm looking for the next point which leads to the lowest in terms of the output right here. I have the lowest output, so this right here must be the absolute minimum. You see how this is an endpoint, this is an endpoint. An endpoint can only be classified as either absolute maximum or minimum or nothing, but you cannot classify an endpoint as a relative or localized value in terms of designation, because they have to be compared to values on either side. At endpoints, you have values only on one side, but not on both sides. The neighborhood values at an endpoint are not good enough that you can do localized classifications or relative classifications. You can only do absolute or global classifications at endpoint. If this right here is absolute maximum, this here is now classified as absolute minimum. This right here would relatively be a good local maximum or a relative maximum. This here would be a local minimum or a relative minimum. This here would be classified as nothing at all. There's no designation for this, because it could have been either an absolute being an endpoint, but it cannot be a relative or localized designation of any sort. So there's no designation for this. Again, absolute maximum, absolute minimum, relative maximum, relative minimum, no classification for this. It's just the endpoint or the initial start of your interval. Keep all of this in mind as we look through this video. When we look through this video, I'm going to go through 3 examples where we'll examine the absolute extrema, the absolute maximum and absolute minimum. I will also bring in along the classifications with regards to the relative or the localized extreme values, if there are any. And I would recommend very much that the video I presented prior to this, the relative extreme values, the local extreme values, the critical points, you must view that before you view this, because there's foundation material in that which you need to know for this. What's your procedure for all of this? Absolute extreme value determination or global extreme value determination. Start by looking at your f of x. That would be your first point, the first step, and examine what you are looking in terms of the general features of that curve. You can do this all in your head, and then take its derivative. When you do its derivative, you're going to do a determination of your critical points. I'm abbreviating that as critical points, and you will also identify your endpoints. This is your initial point, this is your endpoint. Your 2 endpoints are A and B. You're going to evaluate your derivative with regards to this. See if there's a certain critical point when placed into your derivative, the x value of that critical point, if it leads to a horizontal tangent line, or if you have a situation such as this where the derivative with regards to that c value does not exist. You could have either this, you can have either that. They're both acceptable. None of that is nullified if either of these fall into play. The ideal is this. You want to list all your points. List all the points from A, which is your endpoint, to B, including everything in between in terms of your critical points, the stationary points, or everything must be listed. Then you want to evaluate all of these in terms of your f of A, your f of C values, and f of B. into your original function, the very original function, everything is going in there. And this will help you identify your absolute values, your absolute extremes. Then you can do your local extreme or your relative extreme value determinations. And you can do that by utilizing the second order derivative of your function, and in that you'll put in your remaining values for your local or relative extreme value determinations. This is the procedure we'll follow for the 3 examples I'll show you. It may seem overwhelming, but trust me, it isn't. It's actually quite easy. The 3 examples I'll do will be easy to hard. Our first one is this hyperbolic function 1 over x, interval 2 to 4. Let's evaluate this. You want to do the first order derivative, and there's nothing wrong with you doing that. When you do the derivative of 1 over x, you're going to get a minus 1 over x squared. And then you can also do the second order derivative of this. You would be looking at the derivative of minus x to the minus 2. When you do that, you'll have 2x to the minus 3, which will be 2 over x cubed. That's your second order derivative, and we have that in case we need it. You know, when you're doing this, the first step has been 1 over x. You have that, you've analyzed it, you have a hyperbolic function. Second step is a first order derivative. Now look at it in terms of this. You're looking at something like this. If certain value exists which will generate a horizontal tangent line, or are we having a situation where we have a do not exist? When you do this, you're doing minus 1 over x squared, where you'll get a 0 horizontal tangent line. You flip these things around, you have an x squared is equal to minus 1 over 0, and you know that's undefined. So we have this situation existing. What does this tell you? That beyond this initial point and that end point, beyond the end points, we have no values in terms of critical points that will generate either a relative or maximum or a relative minimum. There are no localized extreme values. That's all this is telling you. That does not exist tells you that you only have to evaluate your endpoints. You will only have 2 points to evaluate here, and those 2 points will then get plugged here into your original function. You'll do f of 2 and you'll do f of 4. Now all that remains is to determine which of these leads to an absolute maximum, a global maximum, or a absolute minimum, a global minimum. When you do f of 2 over here, you get a 1 over 2. When you do f of 4, you get a 1 over 4. Which one of these is higher? Remember, this is an x-axis value, this is your y value. You're getting a 2 comma 1 over 2, and here you're getting a comma 1 over 4. Which of these is a maximum value in terms of range? Which is a minimum value in terms of range? Well, this is your absolute maximum because it's a higher value in terms of your range. This here must be an absolute minimum because it's a lower value in terms of a range. If you were to graph it out, a 1 over x, here's 2 and here's 4, you're looking at a curve which would very well look like this, and I'm exaggerating it a bit. Maybe I shouldn't exaggerate it too much. It looks something like this. My value here, the start of the interval leads to an absolute maximum, the end of the interval leads to an absolute minimum, and in between there is no local, there's no relative extreme values. You only have 2 endpoint values, and they're either absolute maximum or absolute minimum, and nothing else in between. And you very well can have situations like this. Consider this as an example, a picture example only. You have a absolute value function which is like this. Part of it from here, let's just say this is minus 1 and this is up to 2. A absolute value, you know, absolute value x. Here you have a value here which will be your absolute minimum. Here you have a value which is your absolute maximum. An endpoint cannot be a local or a relative extreme value. An endpoint can only be an absolute or global value. But if this right here is your absolute minimum and this right here is your absolute maximum, that's nothing. And this is a specific situation here where you have nothing in terms of a localized or a relative extreme value. Everything here is an absolute value. These type of situations very well do arise. Consider this parabolic function x squared looking like this. Let's just say here's 2, here's minus 2. These values here would be your both absolute extreme values. They would be your absolute max, and this right here would be your absolute minimum. Again, there's no relative max, there's no relative minimum. Everything is either absolute maximum or absolute minimum, nothing else. Let's look at this. F of x is equal to x squared minus x cubed from an interval minus 1 to 2. We have to determine all the relevant features of this in terms of extreme values. Let's start with a first order derivative. It will be a 2x minus 3x squared. We can do a second order derivative. It will be 2 minus 6x. Utilize the first order derivative and do that 2x minus 3x squared and make it equal to 0 and solve for x. You have a 2x, and then you have a 1 minus 3 over 2x is equal to 0. X here is equal to 0 and x is equal to a 2 over 3. That tells you there are two critical points. In addition to this and this, there are two other points which may be generating some sort of an extreme value. Your next step is to what? Analyze all of these 4 points. List them out and analyze them with regards to your function. You'll have a, and let's put them in numerical order. You'll have a f of minus 1. Then you'll have a evaluation of f of 0, these x-axis values. Then you'll have a f of 2 over 3. Then you'll have a f of a 2. This right here is my start point of your interval. This is my end point of your interval, a and b, a and b. These are the two critical points we've determined, are critical points. Each of these will lead to something and we have to determine what that is. Everything will come right here. When you put a minus 1 over here, you can calculate it, you'll get a 2. When you put a 0 in here, you're getting a 0 in terms of your output. All of these outputs will classify with regards to some sort of an extreme value. When you put 2 over 3 over here, I worked it out. The 2 over 3 gives you a value of 4 over 27. When you put a 2 over here, it gives you a minus 4. Here's an x-axis value, y value, and you can write them out, all of this. Minus 1 comma 2, 0 comma 0, 2 over 3 comma 4 over 27, and 2 comma minus 4. This right here, you have to look with regards to your y values. This right here is generating an absolute minimum or a global minimum, because in terms of the y value it's the lowest. This here is generating an absolute maximum. 2 is the highest in terms of your y value. This here is going to be a what? You'll have to determine that, and this you'll have to determine. You'll have to determine this now in terms of whether it's either a relative minimum or relative maximum, either or, and we have to do that determination. How do you do that determination? It is through right here. Remember what I showed you in the previous video. When you put 0 over here, the x-axis value here in place of x, you get a 2 minus 0, you get a positive value. So this tells you this right here is a relative minimum. A relative minimum generates a positive. Remember, you're going from minus to 0 to positive, that trend. A relative maximum will be going from positive to 0 to minus in terms of your derivative of your gradient, the second order derivative, and that would be a relative maximum. When you put a 2 over 3 over here, you're getting a 2 minus a 6 times a 2 over 3, but you're getting a negative output. So this right here is going to be your relative maximum, and everything has been identified for you. The minus 1 generates an absolute maximum. The 0 critical value generates a relative minimum. The 2 or 3 critical point value generates a relative maximum, and the endpoint 2 generates an absolute minimum. And let's graph this out for you utilizing these values we have over here. And we won't draw to scale, but we'll try to do it. 0 comma 0, I have a minus 1 comma 2, I have a 2 over 3 comma 4 over 27, and then I have a 2 comma minus 4. I have a graph which looks something like this. It's coming like this and like that. I won't draw it beyond the intervals. Here's my absolute maximum, my absolute minimum, my relative minimum, and my relative maximum, and it's all looking good to me. Our last question, we have a minus x cubed minus 3x squared plus 2 from interval minus 4 to 2. Remember, this is my a and b. Let's start with the first order derivative, because the first order derivative will help you analyze if there are critical points at play. The second order derivative will help you analyze the type of those critical points in terms of localized or relative extrema. But these here will have to be placed in, because when you're talking about absolute or global extrema, you must consider endpoints. This here is a minus 3x squared. This is going to be a minus 6x. The second order derivative is going to be a minus 6x minus 6. This second order derivative equation has to be computed with regards to the presence of critical points. You make everything equal to 0 over here. You isolate minus 3x and you have a x plus 2 is equal to 0, and x is equal to 0 comma minus 2. I have 1, 2 critical points and I have endpoints. And if I'm writing them all in numerical order, I have a minus 4, I have a minus 2, 0, and a 2. I'm going to evaluate each of those with regards to your original function. F of minus 4, f of minus 2, f of 0, and f of 2. I'm doing this to determine what I have in terms of absolute or global extremes. I will then look at everything else which remains with regards to this for relative or localized extremes. When I put a minus 4 in all of this, you can bring out a calculator and you can do it. But when you put a minus 4, you'll get an 18. When you put a minus 2, you'll get a minus 2. When you put a 0, you'll get a 2. When you put a 2, you'll get a minus 18. When I'm looking at this, I'm seeing an absolute maximum in terms of the range. This right here is an absolute maximum. I'm seeing an absolute minimum in terms of the lowest point. that's minus 18, that's an absolute minimum. And now I have to determine what these are in terms of relative or localized extremes, and I can do that by putting them right over here. When I do a f of this minus 2, you're always putting in the x-axis value. When I do that, I'm doing a minus times that, I'm getting a positive output. When I'm doing a 0 in place of there, I'm getting a 0, but I'm getting a negative output. That tells me that this right here, the minus 2, is going to be a relative minimum, and this 0, the critical point of the 0 value, is going to be a relative maximum. And now, utilizing all of this, I can do a graph for you, and I'll do it. The graph will be something like this, but not drawn to scale. I'm going to look at these x-axis values. I have a minus 4, a minus 2, a 0, and a 2. At a minus 4, I'm getting a value here of 18. At a minus 2, I'm getting a value of a minus 2. At 0, I get a value here of a 2. And 2, I'm getting a value of minus 18. My graph looks something like this. I'm not worrying too much about these x-intercepts, but you can see it. X-axis value of minus 4 generates an absolute maximum. X-axis value of a 2 generates an absolute minimum. X-axis value of a minus 2 generates a relative minimum, and x-axis value of 0 generates a relative maximum, and you've seen that, and it's all there. Remember, when you're talking about absolute or global extremes, you have to consider the endpoints. When you're talking only about relative or localized extremes, you don't look at the endpoints, because those relative or localized extreme values are only compared with regards to the values in the neighboring right and the left of that specific critical point. So you never look at endpoints, you look at all of these extreme values inside your interval. But global and extreme values, global absolute values, require you to look at everything, the critical points and the endpoints. And I've put everything here with regards to all the steps you need to do for the absolute determinations and the relative determinations. If there are any questions, just leave them in the comments and I'll get back to you. Thank you for watching. Have a nice day.